Hi, this is example of angle of twist, and last time we talked about angle of twist, trying to define the displacement due to torsion, and that's equal to phi is equal to TL over JG, and T being the internal torque, L is the section length, and J is moment of inertia, G is shear modulus, and so now let's look at this problem. There are 4 torques on here at A, B, C, D, and are they balanced? That's the first question I always like to figure it out. At A, C, and D, they are the same direction, so add them together. 80 plus 60 plus 10, that's 150. That will balance up this 150 at B. So okay, it's balanced. And now the next thing we want to look at is how many sections. So you have AB section, then you also have BC section. Then the last section we'll have is going to be the CD section. So there are 3 sections. And we need to know that 3 sections, they have totally different internal torque. Okay, so let's look at AB section first. If we were cut anywhere between A and B, and you have left and right section, and we'll choose left section, seems to be easier. So if we were cut to look at the left section, and at A, they have this external torque, 80 Newton meter. So this internal torque at where we cut is going to have to be in the opposite direction, right? It's also have to be 80. And to determine if this internal torque is positive or negative, you're going to use your right hand rule. So forefinger going around, and you will realize your thumb is going to pulling to the outside. This is the outside. So it's, outward. If it's outward, that's going to be positive. That's our sign convention for internal torque. Okay, so that's going to be positive 80. Then putting into this equation here for the phi for this segment, we will have 80 and L. L here I'm assuming is going to be 10 meter for AB. BC is going to be 8 meter and CD is 6 meter. So it's going to be times 10 meter. And this 80 is Newton meter. Then we're going to divide it by J. Okay, so J, if we need to figure out what's the polar moment of inertia. So if we assume the radius here is going to be 10, let's see, if its radius is 10 millimeter, okay, so we're going to know, and also we'll give the G, the shear modulus, as 80 gigapascal for this material. So knowing that, we're going to put our J and G here. J will be half pi, our R 10 millimeter and square, fourth. That's going to be our J, and for G, it's going to be 80 gigapascal. So knowing that, we can figure out the phi for this particular segment, but I will hold on to it because you still have 2 sections to go, and those 2 other sections are going to share the same denominator. So I want to simplify it, right? So at BC section, if we were cut anywhere between BC section, you have a choice to look at the left or right. Again, if we go with left, so this is going to be our AB section, that's 80. And since we cut at between B and C, so now we also have this external torque applied at B, 150. Now let's think about at where we cut, what will be the direction? This is 150 greater than 80, so this one have to be share the same direction as 80, and that will give us the value of 70, right? So this is 70, but we're going to see, is this positive or negative? Again, take out your right hand, your forefinger go around this direction, and then you realize your thumb is pushing into this, right? Pushing into the shaft. Remember, going outward is positive, pushing into it, that's going to be negative. So in other words, this is going to be negative 70. So our phi for this is going to be JG. This is JG. And this is going to be negative 70. And times the length for LBC is 8 meter. All right. Okay. The next one is going to be CD section, and again we're going to do the same thing, cut anywhere between C and D, and of course here will be easier to look at the right section, and we will have this way, and that's going to be our external torque 10, and if that's going that direction at where we cut, this is going to go in the opposite direction this way. So feel free to get your right hand out, your finger forefinger is going to follow this direction, and then you will realize you kind of have to twist a little bit your finger here, and then your thumb is pointing into the shaft here again, so that's telling us it's going to be negative value, and it's negative 10. So the phi here is going to be T here is negative 10, and the length for that particular section is 6 meter, so times 6, and JG. Okay, so knowing all of that, and we can figure out this angle of twist added together. So for example, I'm going to be interested to know what's this phi, like for example, D respect to A, you know, one end respect to the other end. What's the angle of twist for this entire shaft? So we're going to use this formula to add them all together, so which is TLJG, right? And you won't realize your TL, it's the same. JG, it's always the same. J is polar moment of inertia. It's going to be pi over 2, and its radius is 5. Radius is 10. So it's 10 and 10 to the power 4, and that's in millimeter fourth. That's our J. And our G, this problem is 80 gigapascal. And then we're going to add all those three sections together in terms of TL. The first T is 80, and L is 10. The second one is negative 70 times A, and the third one is negative 10 times 6. And the unit, this is in Newton meter and times meter. Newton meter, that's our torque, and L is in meter. Now we're gonna figure out the unit. So the top one is giving us Newton meter square. And how about the bottom one? We know gigapascal is in basically kilonewton millimeter square, right? So if we do that, then what do we have? We replace gigapascal with kilonewton millimeter square, then we will get kilonewton millimeter square here after cancel out millimeter square. Then still they cannot be equal, the top and bottom. So we're going to change this kilonewton to Newton. So I'm going to use a different color to indicate my conversion. So it's going to be kilonewton to Newton. That's our first unit conversion. And the second one is this meter, right? Because we can actually change this meter at the top. So this is Newton millimeter, so we're going to go ahead say we're going to have meter here. 1 meter is going to give us 1000 millimeter. Then, however, it's squared up because it's meter squared. So in that situation, you will, at the top one, you will get Newton millimeter square. And at the bottom, you also, once you cancel out the kilonewton, you also get a Newton millimeter square. Then you got your unit canceled out. Then you will get this no unit for phi, which is angle of twist, does not have a unit. So in that situation, if I'm gonna make it better looking, so it's 800 minus 560 minus 60, right? Then we're going to times 10 to the power of 6 because it's 1000 squared. Then over here we'll have pi over 2 times 80, those two terms. And then we'll have 10 to the power of 3 here and 10 to the power of 7, so 10 to the power of 7, right, together. That's going to be our answer. And then you can again cancel out. It's going to be just 10, and the rest is going to be our answer. So I'm actually going to finish this problem. So top one is 180. 180 divided by 80, then divided by pi, and times 2, then we're going to divide it by 10. So my answer here is 0.143. So that's going to be my angle of twist for this problem of D with respect to A. So hopefully you have a better understanding how to solve angle of twist. And again, the sign convention matters here. And tricky part might be the unit conversion. Just pay attention to them. And that's all. I'll see you on the next one. Bye.